Oh, good. Well, there's one of
Both of those are out.
The one at the front seems to be working.
Yes.
I understand. I bet, yeah.
Hey everyone, we're live! No, I'm just about to tweet the link.
There's another one coming.
Wow.
Especially this very good. Somebody will give you anyway, they're going to reattempt today.
Okay, good.
But I will email you support and because we have tools.
Hey Joe, what Wi-Fi are you on?
At your room.
Yeah, what you're on. Cool.
That's exciting.
Yeah.
Yeah, I think it's probably enough if we can just get an extension cord
I guess the more restrictions you have
to let the streaming go.
Yeah, I mean, that's
in the places you want to apply, then
Thank you. If there's also a power restriction, that would be awesome.
yeah,
Yeah.
I mean, there's some
Location was like
some
somewhat
can't be blocked.
Right.
But you know, Jeff Ryan is sort of a hibernation mode.
Cool.
Sure we met, but I know.
Yeah. We should be able to find something.
Can you do it? I only want to very limited. Right. It's like there's one.
So,
Drop down your present. Okay.
Now, this is another.
Here, I can do it. I can do it. From I think you want mirror screens then, right? So you can actually see it on the screen. So what it is
Yeah.
Wait, what is
I
that?
think it just depends
Oh,
on
this
what
screen.
happens.
So I was just gonna test. I signed it onto this computer.
I
Okay.
would type it. Oh, and I guess it also depends on whether or not that's going to interfere with the
Oh,
webcam.
let's see how much it's picking up. I mean, we're getting a huge part of it. Even though the power supply doesn't work, why not move the cable more? If we
That's a good thought.
If we place it here, we get a better angle, right?
Can I have your attention for a quick second? So before we start, this is not related to the conference, but I just wanted to ask for your help in one point then. One problem that I've noticed in what we do is there's a lot of tools that we make that are really cool, but I think we're really bad at communicating it to the industry, or we're really bad at aggregating them in a layperson's understandable terms. So what I'm trying to do is have a blog where it's called Mechanized Game Design, and I'll probably be going to every one of you who has a tool that you would like to share and ask for a short video and a title abstract. And the idea of that blog is aggregating all the game design tools in one place. So if some person in the industry or some person who's getting newly into this field, instead of going on Google Scholar and searching for keywords and trying to parse out 2-column papers, they can just look at the website, see videos. That's a new thing that I'm starting. Right now it's an empty WordPress blog, but please reach out to me and I will probably reach out to any tool-ish thing that I see if you want your tool to be on there. Basically, I'm looking at things that contribute to the game design, game development field in any shape or form. I'm looking for a paragraph and an interactable, a video, a downloadable that can be easily accessible for a layperson. Right, I'm done with my spiel. Thank you all.
Hi everyone, Joe here. Before I get started on my presentation, I just want to actually extend a welcome to everyone who is tuning in via the internet. I know I've been going back and forth on a lot of things this conference, and I just want to say thank you to everyone for showing up. Thank you to everyone who submitted. Thank you to everyone who helped review papers. And an extra special thank out to our co-organizers. Ethan, come on up. Come here. And Alex Zook, who unfortunately couldn't be here today. He's a very busy guy, so.
Don't really have anything to say. Thank you. Welcome. Welcome, whoever's on the internet, the whole internet. Very exciting.
Well, the whole internet, as in the three, experimental AI people who are not here.
That is the whole internet, I think.
Fair enough.
Okay.
I like your view. For those of you, I know I gave this speech to everyone in the room, but for those of you who want to hop on Twitter and talk about this conference, our hashtag is EXAG18. And yeah, we've got a really awesome program of interesting experimental AI talks that we've all put together, and I somehow landed the first one.
Hey!
Oh, and additionally, for those of you at home, if you can't actually hear anything, please say so in the live chat so we can fuss around with that.
Joe, would you like a remote so that you can stand closer to the screen?
That would be beautiful. I was just going to hide over here in the dark.
Actually, I have one of those. Who was this faster on the draw?
Obviously not me.
Hand sanitizer is not it. This is down to the wire. Actually, it turns out that the USB little cord on this came out, so I didn't quite do it.
So, ha!
But it did give the appearance that I
Pass it up quickly!
No!
So how does
The
one
nozzle's
look?
in the bottom.
So yeah, take that out, plug it into the USB cord there, and it should just work.
Yep.
And then log in with your EduRoam credentials.
Always.
There's a slide switch on the side.
Aha! Beautiful. There's a whole setup process happening. Nope.
Looks like it went dark again. From my end.
Matthew, there's a whole identifying your keyboard process happening.
Oh, just push some buttons on the remote.
You can also just cancel out of it.
You should be able to cancel, yeah.
These things lie until the machines their keyboards.
Yeah. True.
Yay!
Woo! Okay. Now that we're done with the experimental technology in games. My speaker notes anyway.
Oh.
It's okay, I'll pace. So, hi everyone, once again, my name is Joe Mazika, and I'm here today to present my research on towards 3D neural style transfer. So, how many of you recognize this image? It comes from a paper by Gaddis et al. On neural image style transfer. What's going on here is this initial image is being redone in the style of a bunch of different paintings. And I remember when I first saw this, I was blown away by this. You've got an image and another image, and you're putting the style of one on top of the other. That's incredible to me. And so my own work focuses on using constraint solving systems to do style transfer on Lego models. Pictured here is my slide from last year's AIIDE presentation that I gave. And so the big thing I do is I focus on style in this three-dimensional domain rather than the 2D that a lot of these neural style transfer papers have been focusing on. So I asked the question, what if we made the jump? What if we took the techniques that have been used to such great success in the 2D case and just applied them directly to 3D models? As you can tell by the title, it didn't quite work out, but I feel that there was a ton of useful information that was gained from this process, so I'm here talking to everyone about it. So here's the roadmap of where I'm going to be going with this presentation. I've got your background information, a voxelized shape, whereas the bottom two focus on more computational creativity, analogy-driven methods. So, fundamentally, when we're thinking about 3D models, one of the fascinating things is just how many different ways we have to represent them. Pictured here, we have the Stanford Bunny, which is a canonical 3D model that shows up in a lot of, frankly, computer graphics papers, but represented in a couple of different ways. You've got a few different wireframes of different resolutions, but over there on the far side, we've got a very interesting one. It's a point cloud. Point clouds represent 3D objects as just a cloud of points. It's a long list of, here are all of the points that we're using to refer to this particular object as just this long string of 3 floating point values. And guess what AI technique is really good at long sets of floating point values? Deep learning. So ModelNet is a collection of point cloud models by Princeton that is just a curated set of point cloud models of 3D objects. And it's used as kind of the benchmark for point cloud classification. So it's got a whole bunch of airplanes and coffee mugs and whatever the heck you want. And your job is to make an AI system that can tell the airplanes from the coffee mugs. And on the left, the left side of the screen here, I've got just a screen cap of their list of systems that have been benchmarked against this set. It keeps going. So we chose to use PointNet, which is a network from 2016, as our neural network that we're using for this neural style transfer. It's got 2 different modes. The classification, it does the classification task where it takes the point clouds and tells you whether or not it's an airplane or a coffee mug, but it also has a mode where it'll take an airplane model and classify the different points into what is the wings, what is the body, etc., etc. So now let's get into what style transfer looks like. Here I have a diagram because I couldn't find any that I felt really succinctly explained how style transfer works. And for now we're going to focus on the 2D case and then bridge the gap into how it might look in 3D. So to do 2D style transfer, we start with 3 images, 2 of which are provided, one of which is just a garbled mess of data, or set all to zeros, or whatever. There is some debate about what you should set this initial image to, but this is eventually going to turn into our output. We take those and we run them through the neural networks. We don't really care what the output is. If we're running Starry Night through an image classification, it might say it's like 25% dog, but that's not important to us right now. What is important is the value of the neural network at a bunch of the different layers. Deep learning is layers on layers on layers on layers of floating point values going through basically generated functions. And I'm sure Matthew's in the back cringing at my description there. But we look at specific layers in the network and compare this noise image to our first image, which has the content. It's the photo we're using. And we also compare the noise image against the second image, which is our style image. And we look at different layers, and then we take all of those values, compare them against each other, and shove them into different loss functions, which we use, I don't have one final slide, to compute how we should transform this noise image to make it slightly less different in content and style from the original two images. Repeat this process on your GPU about 1,000 times, and eventually you have the results we saw at the beginning. So we chose to implement the 3D style transfer in much the same way, just doing a quick find and replace on that previous diagram, replacing ImageNet, or VGG19, which is the network used for the images, with PointNet, and point clouds replacing the images. Here is a diagram of PointNet. Part of the reason we chose it is because, first of all, we have a few little widgets down here. This one lets us ignore rotations. And this one allows us to not care about the order in which the points are in. This is according to the authors of the paper. I'm not quite fully sure how these work. And then finally, we have this whole extra set down here that does that segmentation task I mentioned earlier. So once again, we take 2D style transfer and bam, just find and replace all the bits we need. Unfortunately, it's not so easy to find and replace the loss functions. It was really unclear to us which layers we should look for in both the content and style cases, and also what functions we should evaluate them against to create the gradient to transform the new point cloud to be slightly more like the other ones. So our first experimentation was attempting to figure out what to even look at in this network. So in the 2D case, to get the content loss, it compares the squared sum of differences between the values for content loss, and it takes a grand matrix between layers for the style loss. And this is my obligatory Greek symbol slide. So we consider those loss functions because, hey, they work for 2D, might as well see if they work for 3D. We also consider the Hausdorff and chamfer distances as well. Here's just a diagram of how Hausdorff works. We're basically taking we're taking every single one of the points on X, finding the for each one of these points, we find the farthest point away from it on Y, or yeah. And we do the same for the other one and just take the max of both of these, basically finding the point at which the point clouds are most different, or at least in this case, the point clouds under a few neural network transformations. For chamfer, we're kind of doing the same thing, except for each one of these points, we're just adding up that maximum difference. And that way we kind of get like an average distance between the points versus Hausdorff, which is just the maximum difference. So these are used in the literature to work on point clouds in general. So that seems like a reasonable metric to use. And so now we get into our results. It was unclear, as previously mentioned, what to use in advance, so we tried all of them. Unfortunately, most of our results turned any model we threw at into something like that. Seriously, we had a whole bunch. These are all different. I kept all of the output images and just did a random assortment of dirty snowballs. We had some layer loss pairs that just reproduced the original model, and we had a few that produced twisted models like the one we see here of a soda bottle that's been inverted and squished like I've done to empty ones before. So to figure out the best ones, we start by looking at these results and try to pick ones that line up correctly. So really what we want is a pair that kind of reproduces the initial model for the content, and a pair that produces something inspired by the second model for the style. And so we decided to use a layer that looked like this for style, and one that just reproduced the initial model for content. So in particular, we did the chamfer distance on the third convolutional layer, which is one of the ones in this red box here, to get the content. And we took a Gram matrix and used that to compute the difference for the loss function for style. So this is a blend between an airplane style and a kind of flowy model and address for the content. And as you can see, we've got a couple of different models going on here. It might be kind of blurry on this, but you can it kind of like curls up into a ball, and then eventually you start expanding it back out into the dress. And what these numbers are the different ratios and values between the style and content. When we weight the style really heavily, we just get the results of the style model. When we rate the content really heavily, we just get that. And when we get things in the middle, we're hoping to see this blend, but unfortunately, we're really not. Okay, but what about that segmentation half? So here I have a model of a motorcycle that I ran through the segmentation classifier. As you can see, it does a pretty good job. The body of the motorcycle here is all in the red. The handlebars are in the cyan. You've got the back in blue and the front seat in green. The wheels are in white, and you can go, yeah, no, that's kind of how you would break apart a motorcycle into these classes. This seems like a reasonable job. And so I says to myself, well, since each part of the model is labeled, what if we looked at style in a different way and said, we take the shape of the parts of one model and apply it to each of the parts of the other one, and see how that goes. In this case, our content loss was the distance from the original model. We want it to look as close like the original as possible, but we want each part of the model we're generating to basically be labeled as whatever part it was in the initial model. Again, unfortunately, we just get this weird exploding motorcycle when we try to transform it to look like an airplane. And that brings us to our discussion. So clearly, our approach of throw the 2D approach at the 3D problem didn't work out. But why? A few questions that need to be considered. First of all, what the heck even is 3D style? In 2D, there's this very clear image here where you can see, okay, the style of this matches up with the style of that, and even if we don't necessarily even if we aren't necessarily able to list all of the qualities of the style image that get brought into the new one, I think we could all agree that there is some style that is transferred. Additionally, this isn't the only way we could define this 2D style, but it's very clearly one that works. In the 3D case, we've got no color, no necessarily defined surfaces. It isn't clear what the style would even be. Moreover, once we have a style, we need ways of describing how we combine it with an existing object. If you want to take an airplane and transfer the style of an apple onto it, what does that even look like? I've done a little bit of thinking about this, and coming soon to a paper near you. But it's a hard, interesting, and kind of messy, once you start squishing the apple, problem. Our point clouds carry no color data, and if we go back to the style transfer in 2D, we can see that color is a big part of how we recognize the style of the second one, is Starry Night. And so when we were trying to do this point cloud style transfer, we were really just considering pure geometry. Finally, we have shown that directly applying the 2D style transfer techniques to, in a 3D sense, on point clouds doesn't quite work. There are other systems for 3D style transfer. We've got a pictured results from Kato, Yoshiku, and Harada's neural 3D mesh renderer, which takes a 3D model and a 2D image and just transfers the texture of that image onto the model. But finally, especially because this is the opening paper of EXAG, I just want to go on a bit of a soapbox rant and say negative results papers like this one are important. We tried the obvious thing. Like, it makes sense to just try the straightforward, dumb, and easy method before getting into deeper shenanigans. Granted, it didn't work, but it's important for me to be here to communicate this result not only to the people in the room, but to everyone on the internet, both watching this and reading this paper, that, hey, we tried this, it didn't work. You can skip doing this step when you want to try this yourself. So in conclusion, thank you.
So in terms of what style transfer for 3D would mean, have you thought about like looking at particular sculptures and things like that? And
yeah, that's definitely one of the things I'm considering looking at going forward, because one of the big things we think about when we think about style is the artist or creator behind whatever the artifact is. We talked a lot about the style of Picasso or the style of Rembrandt to pick on European artists, and it is important that we consider, like, okay, what does it mean for, in the 3D case, a particular sculptor to work on things. So one of the things that might be interesting would be to look at particular 3D modelers and see if there isn't like some kind of noticeable style there, or if there are readily available 3D models of sculptures. See how how different artists differ from each other and what that means.
yeah, I mean, for paintings, as you say, you have this nice sort of segregation between style and content, where they're sort of segregated in this spatial frequency domain. And that's kind of an artifact of painting, like brush strokes and stuff like that. One wonders if maybe in the 3D domain, one could look at, I don't know, like horror versus something, some other kind of genre, and are there things there that could be transferred over that would be meaningfully discriminable in something like a point cloud?
Yeah. We should talk more about that.
Okay.
Yeah, I think just quickly building off of Ian's, I'm wondering to what extent is style in 2D really localized, right? Because and localized in the representation versus in 3D. Like, did you play with like reordering the points in the point cloud or something, right? Because I assume that, and I'm not an ML expert by any means, but I assume in 2D style transfer, it's just going through in pixel order. Right?
Well,
is it?
Well, it's convolutional.
yes, it's like
So
patches. It's
patches.
only
So,
local.
So those patches actually contain the elements of style like brushstroke, right? Because it's hyper-localized.
Yeah, so the answer is
3D
yes.
convolution or a 3D convolution?
Yeah.
So this is not, so looking at their paper, they create a symmetric function that is order invariant on the points to, but like, I wonder if like treating it as voxels or something and having a localized thing might
I feel like
be
it's
better.
Yeah, no,
representation
and actually, when I was working on this, it's really easy once you're done doing experiments and trying to write the damn paper to think about more experiments and things to try. And that's definitely one of the things that came up was that notion of localization and like taking these local styles, and if you take a in the 2D sense, you're trying to make it so that it's locally similar to the style, but globally similar to the content. And how does that work in 3D when all you have are these, little points?
Yeah.
And so thinking about like, one of the things I was thinking about was like, okay, what if you just take like a sphere of points and try to make sure that those appear in the output image while still kind of looking like the original one. And there's a whole lot of different ways you can take this. So there's a hand here and a hand in the back, and I think that'll be it for me, unfortunately.
In the examples you showed, you were talking about airplanes and dresses, which to me are quite radically different things.
Yes.
Did you also consider things that are closer together? Like
yeah, but
variations on a dress or variations on airplanes?
so a part of it was trying to dive through and find models, and for me, if I did this on two things that were fairly similar and I got that they blended together similarly, it's like, yes, we can blend two very similar things together. But for me, I'm definitely more interested in taking very disparate things and trying to get them to work well. So I don't actually have any results of blending two very close things in this presentation.
Cool talk. So I have lots of things to say, but there's 2 minutes. So what I'll say instead is all of the 3D objects that you're using here, to me, have the same style, which is sort of like a 3D realistic or semi-realistic style. So is maybe part of the issue here that these things all have the same style, so instead what you're getting is sort of like trying to blend structure versus like if we had like a cartoony motorcycle and a regular motorcycle, doing some blending there might work a little bit better.
Or Art Deco or streamline modern.
Right, anything where it's different ways of sculpting.
Okay. Yeah, that's definitely something worth considering, and actually something I hadn't thought about until just now. I was hoping that getting just two different classes of object would be interesting, but getting back to your point about just blending structure, yeah, that's one of the things we were running into was just like, well, what is the style of these objects, and are they, and where are the stylistic features different from the actual structure features? And so I think you're getting onto something there that might be worth looking at further.
Cool.
And once again, thank you all. I believe Matthew is our next speaker.
Stream dropped like once or twice, but mostly it's been fine.
Okay.
The bigger issue is that you can't really see the slides. I tried turning off the lights, but it didn't really help.
Yeah.
give you back your thing right after this. Okay. It's over here so I can see what it is. I'm going to turn this down, and we're going to see what happens later on.
Let's see what I can do.
Okie dokie. That's fine. All right. That's cool. Yeah, cool. Okay. Hi, everybody. My name is Matthew Guzstyle. I hail from Georgia Tech, specifically the EI lab at Georgia Tech. There's a couple other names over here. I want to pull your attention to this one, Shukan Shah. He's an undergrad who's been working with me. This is largely his work, but I just wrote most of the paper, so that's why my name is up front and why I'm doing this thing. And also, shipping people to Canada is a little expensive. And also got my advisor, Dr. Mark Riddell, there in the background, who helped out. So this work in particular is towards automated Let's Play commentary, and that towards is holding a lot of weight. It's a weight-bearing towards. Let's go ahead and jump into this. So if you're not familiar with Let's Plays or the concept of Let's Plays, typically what's going on is this is a person playing a game, sometimes with a face cam, as you see in the sort of upper corner there. The idea being that they are playing this game as a form of entertainment, sort of like you play a musical instrument, to be able to do all sorts of different possible things they might like to do, but primarily to entertain. And the thing that's going on constantly, even if you don't have a face cam, is sort of a running commentary throughout the Let's Play. And yeah, there we go. So the questions might be like, okay, what's the purpose of this commentary? Why are these people always talking? And one is to do sort of reactions or explanations of game events. So if you want to say like, okay, so this interaction just happened, you may not understand it, but when Mario jumps on top of a Goomba, the Goomba disappears. I'm showing my biases there. The other is to keep audiences engaged through non-gameplay oriented utterances. So this is the fact that games are not constantly exciting. Often they can be frustrating or showing the same sort of thing over and over again. So you keep the audience engaged by just talking about other things unrelated to the game. This is a very small dichotomy. I'll break this down a little bit more in just a second. But first, let's take a look at some examples here. So I'm actually going to jump over to this screen because I actually have to click buttons. I'm going to start by muting, just in case this is terrible. Okay. This is going to be quite a lot. Let's see if I can actually click at the right spots. Ooh, okay. Given this angle. All right, here we go. This is fine. So we do this. I think it's fine.
Flowey the flower.
You're new to the underground, aren't you?
Golly, you must be so confused. Someone ought to teach you how things work around here.
I guess little me will have to do. Oh, this is our tutorial flower. Ready? Here we go.
Whoa, what's happening? See that heart? That is your soul. The very culmination of your being, your moves.
Your soul starts off weak, but can grow strong if you gain a lot of LV. I'm assuming is that like love?
What's the LV stand for? Why, love, of course. Oh, that's sweet.
You want some love, don't you? Yes. Don't worry, I'll share some with you. This could go two ways.
Down here, love is shared through. Through what? Little white friendliness pellets.
Move around. Get as many as you can. Whoa.
All right, so we're going to pause there. I don't want to spoil Undertale for those of you who haven't had the experience of playing through. It's very good. But like, let's think about for a second what's happening in this clip. So there's a lot of just like reading the text on screen, but there's also a lot of reflecting on what's happening. Oh, okay, so I can move. Oh, who's this? Oh, it's tutorial flower, et cetera, et cetera. So that's one major thing. This whole channel is just reactions to things, so this is primarily a reaction-based example. But let's look at a orthogonal example, completely different from this. Okay. I might have to go back over here. No? Okay, cool. All right. let me set this clip up a little bit. So if you're not familiar, there was a character in a sitcom. It was an alien named Elf. This will become important very soon. So this is going to be two people playing Hearthstone, at which point a third person comes in with a Elf soundboard. I don't think this is going to jump to the right point. And as a warning, there's a lot of annoying sounds. Let me make sure. Yeah, here we go. No. Okay, we're going to jump into it. That's fine. All right.
Oh, crap. Oh, that's honestly not that bad as long as misdirection goes off. Okay.
Yeah, that actually might be better for us as long as, yeah, great.
Oh, that sucks because he's immune.
No. Yeah, well, at least we saved ourselves the trouble.
Sure.
And it took 2 damage from the weapon.
That's okay.
We're again with no minions though.
Again with no minions.
We could do explosive trap and kill command, and then
nope.
Or we could kill, yeah, and then no.
That's too much bad.
Oh, we could not. Yeah, it was, yeah. Okay.
Hello.
Hey. Who's this?
Hi, this is Al.
Hey, Al.
Who
Can I
is
help
this?
you? This is Keith, and Art's here too, and we're playing Hearthstone.
What's going on?
We're playing Hearthstone.
Oh, God.
This is Al.
Hey, Al, could you not do that?
But
So this goes on for a lot longer. But you get a sense there of sort of what's going on. Initially, it's just these two people doing this Let's Play, just doing the same sort of thing we saw in the first video, which is reacting to the game, doing a little bit of explanation, talking it through, and then suddenly this completely orthogonal thing comes in, which is someone pretending, sort of role-playing as Alf, this sitcom character. So obviously, Let's Play commentary spans this entire gamut. But there's some interesting things going on here in terms of what Let's Play commentary can do to a Let's Play. And it's helpful potentially for AI systems, specifically guiding users, or audience in this case, through events and explaining those events and keeping the user engaged. So this is the kind of thing we would love for AI systems to be able to do if we could get it working nicely. So that's sort of our main argument, like why try to generate Let's Play commentary? Why is this an interesting AI problem? Is this working again, please? Yes. Okay. So a problem, there's a wide variety of Let's Plays. So this is everything from the reaction sort of explanation thing that you saw in the first video, storytelling and conversation, sort of improvised storytelling or just conversation as you might have in your day-to-day life, sort of like the second video. But there's also things like role play. So there's a little bit of that maybe in the second video, but there's also just entire Let's Plays devoted to just playing as a character in the game, only referring to things in the game, which is, again, a completely different kind. And there's also ASMR, which is basically like nonsense talk that sounds nice to calm you down. There's more to it than that, but that's a nice, clippy title. This is not meant to be a exhaustive listing of all the types of Let's Play, but just to give you a sense of, wow, there's a lot of different kind of Let's Play commentary out there. So this is a kind of tough thing to capture all of it. So our solution to this problem is we're going to use automated clustering to address this variance. The benefits here are, ideally, it's going to pick out the categories of Let's Play, even the ones that we miss, even the ones that we're not thinking of. And it should be easier to learn a distribution for each cluster instead of over the entirety of all Let's Plays. So here's our approach. This is a big, complicated figure, but it is the only one that's big and complicated in this whole talk, so I'm just going to walk you through it. So over here, we have the sort of training half of the approach. We have these instances that come in. They come in as pairs of frames, and then also the commentary that is associated with that frame. So this is like, hey guys, welcome to my Let's Play. And over here, oh no, this is a dangerous spot, etc., etc. We then cluster that with k-metoids clustering with a domain-specific distance function. In this case, we're just representing up here as bags of sprites and bag of words, and we just cluster on those bag of sprites and bag of words. And that gets us a whole bunch of different categories or clusters out of this. Notably, we're estimating k using the distortion ratio, so we're not just like picking a k and then saying like, this is the number of categories there are. We're finding that out automatically. We have some names here on the categories, but that's not important. This is just speculative what we might get. And then for testing, what we do is we pass in just frames. And we then cluster on just these frames, acting as if there were no commentary associated here. And then what we have is a cluster specific, so from the cluster that we cluster this frames into, a cluster specific frame text form. So this is a function. In this case, we're going to use machine learning to estimate this function, where we go from frames to estimated text. So for example here, the true commentary that was hidden for this may have been, shoot, should have avoided that Goomba, when the predicted commentary was, too many enemies, or something like that. And in an ideal case where this works. So let's check this out. So experimental implementations here, we wanted a few different options in terms of our sort of frame to utterance approaches, or this function approximation. So one is random, where we're just going to take a random training sample and return it, its utterance for the given test input. One is forest, or 10-tree random forest. So this is predicting from frames to just text string represented as a bag of words. So not a string actually, just a bag of words. We use a 200 max depth to ensure generality. And a KNN, in this case we have a 5 and 10 k nearest neighbors. We're going to predict on bag of words be just swooshing together bag of words. So notably, anybody who knows me knows that I love Super Mario Brothers, clearly, because I use it all the time. That's the reason why I use it, clearly. And not just because it's around. So what we did is we grabbed 2 Let's Play videos of Super Mario Brothers from the same YouTuber. We used the automatic transcripts from YouTube to get the transcripts out of that and just pair that with the frames. We had 1 video for training data and 1 video for testing data. This is very initial, obviously. This is not nearly enough data for most sort of machine learning approaches, but all the approaches we're using are fairly low cost in terms of data required. So let's take a look at how this works. We're going to run 2 experiments. Here's the first one. For the first one, the question is, do the clusters actually help? So we created 2 variations of each of our approaches. Standard, where we just train them as you might assume we would train them. So we take the entire training video and train the random forest and the KNN approaches on the entirety of everything from the training video. The per cluster approach instead is that figure I showed you earlier, where we're going to cluster everything first, and then we're going to learn a function approximation of these, this forest and these KNN for each category, every learned category or cluster. So here's some results. This is cosine distance as the test error, and so lower is better. So we can see that our per cluster approach in general is getting the lowest scores, which is great. Notably, the best performance is comparing the random forest for standard versus per cluster. There's a pretty major improvement there. There's not nearly as extreme an improvement for the KNN 5 or KNN 10, but that makes sense if you think about k nearest neighbors. We're just already sort of approximating these clusters by just grabbing the closest points anyway. So it's similar there, but the fact that we have any improvement at all is a positive sign. Okay, so then experiment 2. From that first experiment, you might say, well, I know machine learning, and I know that dimensionality reduction just tends to improve performance regardless. So maybe it's not the case that you had these clusters were like true categories. It's just that there was less stuff going on, so it was easier to learn. So what we did for a second experiment was we compared the true predicted cluster to a randomly predicted cluster, just to see if that was the case. And here's the results here. Once again, cosine distance to lower is better. And true cluster generally wins out. For random, it's very close, but it's random, so that's okay. The fact that we're just selecting something at random, it's not a big help. Again, biggest improvement is on the random forest, which makes sense compared to the KNNs.
Quick question?
Yeah, sure.
Do you really mean lower is better?
Yeah, because it's distance. So we want less distance compared to the test values.
Okay, but the cosine can only go up to 1, right?
Yes, so yes. But so it's 0 to 1 in this case.
is the variance. So we're getting 0.885, et cetera. So it's a pretty high distance still in terms of the test predictions. So again, like the exact values are not great here, it's just the relative values. All right. So here's a brief qualitative example. No, we only have a single qualitative example, which should give you a sense of how well this is working. So here's the test frame. The hidden true commentary is if you get to Bowser. The system prediction using a canon of 1, which allows us to just predict a single output sentence, as opposed to just random bag of words, is grabbing this frame and saying parts like these on Bowser. So this is the interesting thing that's happening here. First of all, there's not a Bowser in either of these frames. So maybe the system is getting something about like when the player is in underground levels and just sort of wandering around, this person tends to talk about Bowser, maybe. But this also could just be random noise. But the fact that we have this sort of relative performance of these individual experiments suggests we do have something going on here. So some limitations. We're not using state-of-the-art natural language processing or generation. If we were, then we would expect improvement, but we would also need a larger training data set. And this was just an initial thing to test out the initial assumptions we were making about the variance of Let's Plays and how to address that. We only use 2 videos. Again, we would like to use a larger set if we were actually actively trying to solve this problem instead of just trying to evaluate these initial assumptions we were making. The initial results are not great. They're promising towards the assumptions we're making, but not great in terms of actually being Let's Play commentary. Some quick takeaways. Let's Play commentary is an interesting domain for PCG and sort of general AI studies. Let's Play utterances vary a lot, and so a successful approach must handle that variance. This is one suggestion of how you could do it, but there's lots of other ways. And Let's Play commentary generation is possible, but hard, as you can see, because this initial thing got what we got. So some quick thanks to the NSF for helping support this research, and to Shukan Shah, I just want to call him out once again for doing some really cool work on this. And that's it. Happy to answer any questions. Thank you. Go for it.
So I have 2 questions. One is, you mentioned in one of the slides, successful. So how is exactly success defined here?
Relative success to the sort of counter we were putting forward for each of these experiments.
So through a user study, like who wants to see your Let's Play commentary versus human?
Oh, you mean just like generally, like what would it mean to be successful?
Yeah, what would it mean?
Okay, got it. Yeah, so that's a great question. We do think that it would require a human subject study. I don't think there's an automated approaches to my understanding that can sort of evaluate Let's Play commentary. We could use some approaches that have been used for natural language generation, just to get a sense of like grammaticality and things like that, to give an initial baseline, but to really check, we would need a human subject study.
Again, a second question was, so you mentioned earlier in your talk that part of the reasons to do it is to keep the audience engaged when there's some downtimes in the game or frustration or whatnot.
Right.
So that reminded me of sports. So in color commentary in sports, let's say baseball. So you mentioned in your paper related work in the past, but I didn't see it in the talk. Can you talk a little bit about why something like scores wouldn't quite do this?
It's a great question. So the thing that's going on with scores or similar sort of systems to it, which are about like, here's a set of events and now let's generate commentary based on those events, is you have that initial like ground truth, what's happening, right? And for the Let's Play commentary, we just have video. We don't have access to the game engine. We could if we were using this in a different way, but right now we're assuming we just have video. So we don't have ground truth, what's actually happening. So that's the major difference between that. Go for it.
Did you consider, right, like image captioning is like a thing that people do, and like this is, at least in the context you're doing, somewhat similar, right? You have an image and you're captioning it with like what the person has said. Is there a reason you didn't go with sort of the current, popular neural approaches for image captioning?
So I can give you like a fakey science answer, which is like, well, we wanted to start small and you build up, etc. But really, this was like Shukan's like one of his first projects, and so he's just not familiar with deep learning and these various other state-of-the-art stuff.
And I guess slightly follow on. Sorry. right, like the commentary is like, you know, a stream that's going on,
right,
and like you're treating it as like a single image.
Yep.
And
well, it's actually like a sequence of frames, but yes.
Okay, but also you're not generating commentary in the context of previous commentary that you have said.
Yep.
So
in the paper we talk about, we assume that any true attempt at this would need to feed in not just the current frames, but also prior frames and prior commentary to make sure that it's consistent.
Okay.
You're totally right. Let's jump over here and then we'll jump back this way. Yeah.
So this is a really cool idea. I like it a lot. One thing that struck me when you said, you know, Let's Play projects have deeply varied utterances.
Right.
Sometimes those utterances are like deeply offensive.
True.
Right? And either in a sort of easy to filter through stop words kind of way, or a longer ranging narrative.
Sure.
Have you put in any thought in how you might try to address that?
Right. So currently the way we're addressing that is just by being very selective in terms of who we grab as Let's Players. So we're not going to grab like, I don't know, like Ninja, Dr. Disrespect, name your least favorite streamer of the week. But you're totally right. Like this is an ongoing problem of like how do you avoid it from saying bad things? And we're not there yet.
Only train on not bad people.
For now. But again, like that's not a perfect solution. Hold on, let me get over here and I'll come back. We have plenty of time. Go for it.
So my understanding is that the input is sprites. Is that correct?
Yeah, so right now we're using a bag of sprites representation. So we're using OpenCV. I didn't mention that in here, but we're using OpenCV to just like grab out the individual sprites in each frame.
What's your intuition on using a image classifier to see what class of objects there are, or maybe in OCR recognition of like, it says game over, that's an important input that is easier to catch with an OCR system.
Sure.
To add or enhance the whole pipeline, would you say?
Sure. So there's lots of better ways of doing image processing and sort of representation than we're currently doing. In current work, we've actually moved to just raw pixel input, just because that's the most generalizable as long as we're using video, right? But you can imagine definitely that something like that, giving it that extra information would be really helpful, for sure. Yeah.
So you just mentioned like Ninja and Dr.
Yep.
And they are not Let's Players, they're Twitch streamers who like are also in conversation with their chat, which is very different than a Let's Play thing. So have you thought about how you would handle the differences between like Twitch and like a static video like on YouTube?
Right. So far, no. I was using that example more in that they are by far like more famous at the time.
Sure.
Right. There are definitely bad YouTubers as well, who are primarily YouTubers and not streamers. But yes, you're totally right. This adds a whole other dimension of this problem of like what is currently in the chat as needing to know if you were actually to respond to that correctly. So it's like a whole other ball game that we haven't gotten to. Yeah.
So in the clustering, you mentioned that, or in the diagram at least, you showed like some example categories that you might be getting out. They were like combat, introductory, things like that. And so if you're training on one video for like an example level, then those categories are all kind of discrete, right? But if you have maybe two different streamers or two different Let's Plays of the same game or of the same video, then they might be giving conflicting commentary for the same part, right? So have you considered how, I guess in addition to the clustering, how you might be able to separate out like what's like the actual commentary that's related to the game and what's the commentary that's just filling space, basically?
Yeah, that's a good question. I don't have a great answer. The answer we're using is basically the typical machine learning answer of like, given sufficient information, a large enough representation, which does sound like the start of a song. But no, like you're totally right. Like there's a lot of contradictory stuff going on here. That's our main point trying to get across. Is like these things vary a huge amount. But the hope is, right, if you have both the text or the utterance that's currently happening, previous utterance, and the current frames, that you can both figure out when are these things similar, when can you generalize, so like both complaining about a similar enemy in a similar way, versus like these are two completely different stories from two completely different people. Yeah. Oh no. All right. Okay. Cool. I think we're good then. Thank you all so much.
All right, and with that, it is time for our first break of the day. So the stream's going to go down while I futz with some settings and hopefully can designate someone to grab me whatever snacky things they have.
Designated.
And then we'll be back in about a half hour with the next set of talks.
Joe, is it okay to leave our stuff in the...
I mean, I'm not